Welcome to the deep dive. Today, we're jumping straight into something really fundamental to how computers see and represent space. Pixels and voxels.
Right. We've got some lecture materials and a briefing doc here that really unpack how these structures work for spatial info.
Yeah, and if you've ever wondered, how your phone shows an image, or how maps work digitally, or even 3D models.
Then you're already dealing with pixels and voxels, even if you don't think about it that way.
Exactly. So whether you're maybe prepping for a design meeting, or just trying to get a better handle on computational design stuff.
Or maybe you're just curious. We're basically going to break down the key ideas, keep it clear, hopefully not too overwhelming.
That's the plan.
Yeah.
We have this lecture transcript, a professor walking students through these concepts, comparing them to graphs, which is helpful.
And there's also a briefing document that kind of summarizes the main points.
So our mission today is to pull out the really insightful bits and, connect the dots so it all clicks for you.
And that comparison to graphs is actually a great starting point. The lecture brings it up right away.
How so?
Well, think about graphs like a subway map. They're great for showing connections between distinct things, right? Like different stations.
Okay, yeah. Discrete points and links.
Exactly. Pixels in 2D and their 3D cousins, voxels, do something similar but for spatial information, especially when that information is like continuous.
Continuous meeting.
Things that change smoothly across an area, like light intensity or the quality of soil, or even mapping social data across a city. Pixels and voxels help us represent and analyze that kind of stuff.
Got it. Okay, so let's get into the nuts and bolts then. Pixels and voxels and these core spatial structures.
Right. So a pixel, at its most basic, is just one tiny square of color in a 2D image grid. Think mosaic tiles.
Okay.
And a voxel. Well, it's the 3D version. Imagine taking those squares and making them tiny cubes. You stack them up and you build a 3D space.
Almost like digital Legos or Minecraft blocks.
Precisely. That's a really good analogy. The lecture actually mentions 7, 8, and 9th weeks about how to deal with the special information using MashGraph and Pixel Bookit. Bookit, probably meaning voxel here, which we will learn today.
So it's positioning them as fundamental tools alongside things like meshes and graphs that we might already know.
Exactly. And the lecture highlights their versatility, too. It says, so basically we can have a multiple layer along the z-axis, like 2D layer.
Ah, so you can stack information.
Yeah.
Yeah.
We can capture the sun value while time over the year or day. And also we can apply some quality of the soil.
Okay, so different data types and layers.
Right. Maybe if you guys are interested in like social information, you can map some social. Basically, we can process all this spatial information. It shows you can layer all sorts of data within the same spatial grid.
That's pretty powerful. Sunlight, soil, social trends, all in one structure.
It allows for really complex analysis, looking at how different factors interact in the same space.
Now, you mentioned that key difference from graphs, discrete versus continuous data. Let's unpack that a bit more.
Okay, so the lecture puts it quite clearly. So basically, if you want to deal with the discrete information in space, then graph is the data structure you want to use it.
Makes sense, right? Nodes of connections.
Yeah, distinct things.
And on the other hand, the pixel map, same as the graph, but we can basically consider this one as like continuous data processor. That's the key phrase, continuous data processor.
Okay, so what does that really mean in practice? How does it process continuously?
Well, it means you can represent stuff that changes gradually. The lecture gives this example, like if something bad happens in one spot, its effect probably doesn't just stop abruptly at a boundary. It likely fades out.
Yeah.
Affects the surrounding area to some degree.
Yeah, like ripples in a pond.
Exactly. Pixel data can capture that smooth gradient of impact. A graph, with its distinct points, struggles more with that kind of smooth transition.
And you mentioned interpolation before. That fits in here perfectly. Because you have values at grid points, you can actually estimate the values between those points. You can interpolate.
Filling in the gaps.
Right. Which gives you a much smoother, often a more realistic digital picture of whatever continuous thing you're measuring. No sharp artificial jumps between data points.
Okay, that makes sense. But how do we get, real world stuff, which is often analog, into this digital grid format?
Good question. It's about discretization, basically. turning analog signals into numbers.
Like sampling sound.
Exactly like sampling sound. A sound wave is continuous, but on a computer, it's stored as a series of numerical samples taken at specific moments.
Okay.
Same for images. An image in the real world has, theoretically, infinite color variations, but digitally we break it down into a grid of pixels, and each pixel gets assigned a specific number or set of numbers.
Like a grayscale value from 0 to 255, maybe.
Yep, or RGB values, red, green, blue numbers for a color image. We turn the continuous into discrete, countable values on a grid.
Which brings us to resolution. More pixels, more detail, right? But there's always a catch.
Always a catch. Yeah, the lecture points this out. So there is always a resolution problem. Higher resolution, so more pixels or voxels, means finer detail, absolutely.
Right.
But it needs way more memory and way more processing power. The lecture says if we have infinite memory, there wouldn't be a resolution problem, but that's impossible with computing power and memory.
So it's a constant trade-off. Detail versus cost, essentially. Computational cost.
Exactly. And this trade-off, this grid structure itself, can create visual artifacts sometimes.
Like jagged lines, aliasing.
Yeah, that's one. When a smooth diagonal line has to be represented by square pixels, it can look stepped or jagged. Anti-aliasing techniques try to smooth that out visually.
And what about those weird, more R patterns you sometimes see on screens?
Ah, yeah, the lecture mentions those too. When you render grids on the screen, it creates different patterns. These are called Moore patterns.
How do they happen?
It's usually an interference pattern. It happens when the grid of the screen pixels interacts strangely with a grid or pattern in the image data itself, especially when things are scaled or compressed.
Okay. So we've got the data in the grid. Now, how do we actually work with it? The lecture talks about kernels and filters. Sounds technical.
It sounds technical, but the idea is pretty intuitive. Think about photo filters on your phone, like making an image sharper or blurrier.
Okay.
Digital kernels and filters are kind of like that, but they're doing math. A kernel is usually a small grid of numbers, like a tiny stencil.
This feels like.
Yeah, this little grid or kernel slides across the whole image, pixel by pixel. At each position, it looks at the pixel underneath it and its neighbors.
It does.
And performs a calculation based on the numbers in the kernel and the color values of those pixels.
Yeah.
The result of that calculation becomes the new value for the center pixel in the output image.
Ah, so it modifies the image based on local neighborhoods.
Exactly. And different kernels, different sets of numbers in that stencil do different things. Well, the lecture says, if you apply filters, you can detect horizontal and vertical edges. So some kernels are designed to highlight sharp changes in color, which correspond to edges.
Okay.
Others might average the values of neighboring pixels. What would that do?
Smooth things out, blur it.
Precisely. Averaging creates a blur effect. So these kernels are just mathematical tools for processing the pixel data to enhance features, reduce noise, detect patterns, and so on.
Got it. Now, color itself, you said it's a data structure. The lecture mentions different color spaces, RGB, LAB, HSV. Why so many?
Well, they represent color differently, and each space is useful for different things.
Yeah.
RGB, red, green, blue is what your screen uses. It's additive light.
Right.
But RGB isn't always great at representing how humans perceive color differences. So spaces like LAB were designed to be more perceptually uniform.
Meaning a change in the numbers corresponds more closely to how different we see the colors.
Exactly. And HSV hue saturation value is often more intuitive for things like picking colors. YCBCR is used a lot in video compression. They're just different mathematical ways to define a color.
And the lecture stressed the idea of distance between colors.
Yes. So when you look at this right now, you should feel distance. Distance. All algebra looks at distance. Because these spaces are mathematical, you can calculate the distance between 2 points, meaning 2 colors.
And why is that useful?
Oh, tons of reasons. Image analysis find all pixels close to a certain color. Design create palettes where colors have specific mathematical relationships. You can use standard distance formulas like Euclidean distance within these color spaces.
Fascinating. And we could do calculations with color, too. Additive versus subtractive mixing came up.
Right. Additive is RGB mixing light. More light equals brighter towards white. Think screens.
Okay.
Subtractives like paint or ink, CMYK, cyan, magenta, yellow, key black. Mixing pigments absorbs more light, gets darker towards black, think printing.
And this relates to blending modes in Photoshop, like multiply or screen.
Absolutely. Those modes, as the lecture explains, are just different mathematical operations applied pixel by pixel between layers. Multiply darkens because it's like multiplying fractions. Color values often treated as 0 to 1. Screen lightens.
So it's all just math on the pixel values again.
Pretty much. The lecture showed examples using blending modes to add lighting or shadows realistically to photos just by calculating color changes.
Cool. What about this force color or pseudo-color idea? Mapping data to colors that aren't real.
Yeah, that's a really powerful visualization technique. Sometimes the actual colors, or just grayscale, don't reveal the important patterns in the data.
So you assign arbitrary colors.
Not arbitrary, usually a specific spectrum or gradient. The lecture says the reason why we want to use force color is because we want to see the difference along the scale.
To exaggerate or highlight subtle variations.
Exactly. Think of a thermal camera image. Hot areas are reddy yellow, cool areas are blue purple. Those aren't the actual colors, but the color mapping makes the temperature differences immediately obvious. That's force color.
Okay, that makes sense. And sometimes there's just too much information in an image. How do you simplify? The lecture mentioned dominant colors and histograms.
Right. An image can have millions of pixels, potentially thousands of slightly different colors. A histogram just counts how many pixels of each color or colorway there are.
Like a bar chart for colors?
Pretty much. The peaks in that histogram show you the dominant colors, the ones used most frequently.
And that's useful for?
Understanding the overall feel of an image, summarizing its palette, maybe for image compression, or even classifying images like finding all images with a predominantly blue palette, it simplifies the complexity.
It seems like whether we're talking graphs or pixels or voxels, this idea of connection keeps coming up.
It's fundamental. The lecture really hammers this point, but the key is that there is connectivity. In fact, if the information is not connected, it's meaningless.
So isolated data points aren't very useful.
Generally, no. It's the relationship between points, whether it's an explicit link in a graph or the implicit neighborhood relationship in a pixel grid, that lets us analyze and understand the data. Think about BIM in architecture.
Building information modeling?
Yeah. The power there isn't just the shapes, it's that the system knows this wall is connected to that floor, which supports that beam. It's the embedded relationships. Compare that to just drawing shapes in, say, Rhino, where they don't inherently know about each other.
Right. So connection gives context and meaning. Now, how do we analyze patterns across space? The lecture mentions spatial binning.
Yeah. Binning is basically a way to aggregate spatial data. You overlay a grid, often squares or hexagons, onto your area of interest.
Okay.
And then you count how many data points, like crime incidents or trees or customer locations, fall into each cell or bin of that grid.
So you get a density map.
Exactly. It helps visualize hotspots and patterns of distribution. The lecture specifically mentions hex bins using hexagons instead of squares, which can sometimes give a more visually balanced representation.
We talked about interpolation earlier, estimating values between pixels. Why is that so important for pixels voxels compared to graphs?
Because pixels and voxels are usually representing samples of something that's actually continuous in the real world, like temperature or elevation. Graphs often represent discrete entities.
Right.
So being able to interpolate to smoothly estimate the values between the sample points is crucial for creating a realistic digital model of that continuous reality. The lecture notes this is a key difference. We don't need to worry about interpolation between node and node in the graph, but the pixel or buccal value, because we want to convert real information into the continuous form.
It lets us model things more fluidly.
Yeah, you can even apply concepts like attractors or repulsors that influence values across the grid smoothly, which is harder with discrete graph nodes.
And we touched on layering information earlier. That seems like a huge advantage of these grid structures.
Definitely. Especially with voxels in 3D, you can have a layer for soil type, another for water content, another for, I don't know, underground infrastructure, all aligned in the same 3D grid.
And analyze how they all interact at specific locations.
Precisely. You can query the voxel grid at any XYZ coordinate and get the values for all the different data layers at that exact spot. It enables really sophisticated multivariable spatial analysis.
It's interesting that even though these are grids, not graphs, the lecture mentions using graph algorithms like BFS and DFS. How does that work?
Well, you can think of the pixel or voxel grid as a graph, in a way. Each pixel voxel is a node.
And its neighbors are connected nodes.
Exactly. So algorithms designed to traverse graphs, like breadth-first search, finding the shortest path, or depth-first search, exploring branches, can be adapted to work on these grids.
What would you use that for?
Finding connected regions of the same color, maybe? Like identifying a tumor in a medical scan. Or finding a path through obstacles in a game map represented as a grid. Or simulating the spread of something across the grid.
Okay, so the algorithms can translate. And moving from 2D pixels to 3D voxels, is it just adding a dimension?
Fundamentally, yes. The lecture puts it simply. So we are just adding it to 3D. Only the connectivity changes. The rest is the same.
So instead of 4 or 8 neighbors on a plane.
You now potentially have neighbors above, below, front, back, left, right, up to 26 neighbors in 3D space, depending on how you define connectivity. But the core ideas of storing values, filtering, interpolating, they all extend quite naturally.
This allows for true 3D analysis then, like medical scans or...
Or simulating sunlight on a building model throughout the year, or analyzing airflow, or mapping geological data underground, anything that has spatial variation in 3 dimensions.
The lecture used a great analogy here with video games. Pac-Man, Minecraft.
Yeah, it's a brilliant way to think about it. Pac-Man moves on a 2D pixel grid according to simple rules. Minecraft builds worlds out of 3D voxels, again with rules about how blocks interact.
So the games are essentially rule-based systems operating on these spatial data structures.
Exactly. And look at the complex, engaging results that emerge from relatively simple rules interacting on that grid. It shows how we can abstract complex processes, even design processes, into rules operating on special data.
And that often involves iteration, right? Letting the system run.
Very often. Think about simulation. You set up initial conditions on your grid, define rules for how cells or voxels change based on their neighbors, and then you run it step by step.
Like Conway's Game of Life.
The perfect example, mentioned in the lecture too. Very simple rules about cell survival lead to incredibly complex, sometimes unpredictable, evolving patterns on a pixel grid. Many computational design techniques use similar iterative, rule-based approaches on grids.
And finally, bringing it back to concrete applications, remote sensing and GIS.
Yeah, absolutely fundamental there. Satellite images, aerial photos, they're pixel grids. Geographic information systems rely heavily on pixel data, often called raster data in GIS.
So when I zoom into Google Maps,
You're seeing pixels, and the color of each pixel represents information. Is it water, forest, urban area? What's the elevation? The lecture notes how the zoom level relates directly to the real-world area covered by each pixel.
so wrapping this all up, what's the big picture here, the main takeaway?
I think it's that pixels and voxels aren't just, static pictures or blocks. They are powerful, dynamic data structures.
Right. They let us represent, analyze, and actually manipulate spatial information in really flexible ways.
Exactly. They're this crucial link between the physical, often continuous world and the digital realm where we can compute things. It opens up just a huge range of possibilities in design, science, engineering.
And for you listening, getting your head around these basics, thinking in grids, understanding continuous data representation, the idea of layers and filters, it really builds a strong foundation.
Yeah, it helps you tackle more advanced topics in computational design, data viz, spatial analysis. It just gives you a different lens to see how digital tools understand and interact with space.
So maybe a final thought to leave you with. Consider just how many technologies you use daily that depend entirely on pixels and voxels. Your screen, sure, but also medical scans, weather forecasts, mapping apps.
Yeah. So how could understanding these underlying structures, really seeing the grid, the data, change how you interpret the information you get from these tools? Or how you might approach designing things yourself? What new ideas pop up when you view the world not just as objects, but as these intricate fields of spatial data waiting to be explored?
Definitely something to think about. We've covered a lot, but really just scratched the surface. The source materials we mentioned have even more detail if you want to dive deeper.
Yeah, try looking up different color spaces or maybe find some simple image filter examples online. It's fascinating stuff once you start playing with it.
Absolutely. We encourage you to explore further and see how these ideas connect to what you're working on or interested in.